Hey there, in this recording I'm going to describe how the PySpace theory calculates an orbit. Um, the idea of this algorithm is that it's a general solution to orbits. Typically the Newtonian approach, which you can use and it works quite well, is to solve for various different components such as the distance one travels or the speed and so on. Now you can use those formulas in the PySpace theory in the advanced formulas section, but this document is trying to and implements an algorithm which calculates each position in time, and then from that position it moves on to the next position and so on. And you can run the algorithm as much as you want, putting the results in from the previous position and so on. And then depending on your requirements, you can solve for distance or time or position or whatever it is that you need to calculate. Uh, so the diagram here highlights the approach. The algorithm is designed in a way to also take into account intense gravity fields, which cause the warping of the the orbit, unlike in a weak gravity field such as on Earth. So primarily where the space time is not warped. So it's designed in a way to calculate both to take into account both situations. The the kind of the extreme case would be a light particle traveling through some kind of a strong gravity field and getting warped by it, which was shown by the Einstein work. But the majority of the uses of this algorithm, I think, would be just to try and predict the next position of an object. So the way it works is you have an object which is positioned at x1, y1 with regard to a center of gravity, and it's a distance r from it. The gravity field has an established gravitational constant, which is calculated based on the mass of the object and the radius, um, which is calculated in the algorithm. Uh, each time that the object moves, it moves closer to the gravity field. This is its starting position. It moves closer to the gravity field, in this case by zero point 0.5 times at squared. And then the object that is moving, has a momentum, which is v times t, mvt. But for the diagram, we just highlight the velocity component, so the v times t. So it moves to v times t. You have the attraction towards the gravitational field, and this gives you the next position, and then this gives you this distance u, and then you have this new position, and then this new position then becomes the next position, and then it goes down by a half at squared, and it has v times t, and then you move to the next position and so on. The algorithm will calculate will continuously update the distance from the center of gravity. We have to calculate the distance s, which then becomes the next or, and you keep running the algorithm so on as many times as you want. Now, in terms of the diagram, this triangle here is this one here. This is a more a sort of a kind of a larger close up of it. So we have a 0.58 t squared. We have it at v times t, and this is the angle with respect to gravity that you would say see the object move at, or if you were throwing it or whatever. Internally, the algorithm has to calculate alpha and beta. It has to calculate the value u, and it has to use the sort of law of the cosines, law of the sines, and so on to calculate that. Now, the way it also works in the algorithm is it breaks out the x and the y velocities, and it keeps updating those. The v times t x and y velocity stays constant, but this interacts with the field, and therefore you end up with the orbit. So the way that there's an algorithm which has approximately 21 steps, and I describe it here where you choose x1, y1, moving with velocity v under acceleration a and angle theta with respect to the gravity field, and the center distance from the gravity or an angle offset 0. with respect to the axes. Typically, that the angle the O is zero in a kind of a case around the surface of the planet. And I just talk here in the algorithm how it's calculated. I break out the x and the y velocities and so on. The algorithm will calculate the acceleration a at each point because it varies depending on the distance you are from the planet. So you'll need to know the mass of the object. You'll need to know the gravitational. You have to calculate the gravitational constant, and you'll need to know the mass and the distance you are from the center of gravity. So you calculate the A. So this is the Newtonian formula. And then a variety of calculations then occur. And the interesting point is they use the law of the cosines and they use the law of the sines. And I also calculate the curvature angle here using the law of the sines. Now the code is actually implemented in on an open source project I have, and I'm not going into that in this detail in this discussion. I'm just going to talk about the theory. So this is part one. So this is the theory part, and this is the algorithm. At the moment, the code is up on the PySpace Physics software location on SourceForge at the time of recording. So just to give you just to kind of the diagram is really what the steps are calculating. So it's basically a series of triangles where this VT is constant. This is the conservation of momentum interacting with the field effect, and you just calculate the different angles and so on, and you just work with it. It's an idealized example that doesn't take into account like air resistance or any of that stuff, or the wind, or the angular momentum of the planet or anything. But it's basically an idealized version of the Newtonian work with some PySpace and some relativistic amendments, and that's it. So that's how the document lays it out. This document is called this is called Calculating Orbits in PySpace. This is the Calculating Orbits in PySpace document, and it's part of the PySpace theory. In part two, I plan to show the code, and plan to show the code how it works and show some examples. That's it. Thank you.